so this is a problem transformation. If we see an assignment, x gets A, where x is not live after the assignment, then we replace it by skip. I mean, we could, morally, we are removing it completely, but it's easier to just rewrite a command to a command. And so other assignments will stay the same, and loops and if then else and so on will stay the same. So it's a simple function, DCE, that code elimination, that takes a command, that takes the live variables after and returns the optimized command. Again, it's easier to show that under Coq development. Okay, so it's pretty short. So skip stays at skip. Assignment is preserved if x is alive after. Otherwise, it turns into skip. And for a sequence, well, we reconstruct the sequence. We simplify in C1 and in C2, and we reconstruct a sequence. The only gotcha here is that L is the set of variables live after C2, but for C1, it is live C2L. Okay, so we have to update that information L, what is live after, during that computation. So if then else becomes if then else, and while, again, we simplify the body, again, with the proper set of variables live after.
So
yes, please.
Slight improvement.
Mm-hmm.
In that while, you said while B do C prime, then the part where you invoke the live function, you could just appeal to the C that came in, the C from above, and match C with. So you wouldn't have to reconstruct the while loop.
If DCE does nothing.
Yes.
But DCE does something about C. It's going to remove assignments, dead assignments that are inside.
Oh, sure.
Okay.
So that needs to be the C prime as well.
Oh, okay. You mean this one?
Just that one.
Oh, yes. You're right.
Just that.
You're right. Yeah, it's a good idea not to name everything C. That's a good point. Well spotted. Other questions? Yes, please.
So why in the sequential case?
Yes.
Why don't you check liveness after you remove the dead code?
Why don't I check the liveness after? Oh, you mean here?
Yeah. So
That's a good question. So I believe, but that would deserve a proof, that the liveness computation we've done is actually insensitive to DCE. So just because we've anticipated this removal of dead assignments in the computation of the liveness, I think that the live CL and live DCE CL are the same. But that would deserve a proof. That's a nice exercise. Thank you. Okay, so let me show you this transformation in action. If I can. Well, I don't know. Yes. Too many choices, you know, when 7 choices pop up. Okay, is it working or not? It is. Slowly but surely. Okay. All right, so here I'm defining a little program. So I'm giving some names, A, B, Q, R, to a few variables. And so this is a program I'm going to consider. If you squint at it, you will see that it is actually Euclidean division by repeated subtraction. Okay. So we divide A by B, and at the end, Q must be the quotient and R must be the remainder. And here's a cool example. Let's say that actually we are using this computation in a context where we don't need Q. We don't need the quotient. All we need is a remainder. So let's optimize this, saying that R, the remainder, is live after this loop, but not the other variables. And here is what we get. we get a program that, so you see this assignment to Q was turned into a skip, and this assignment to Q was also turned into a skip because there's no need to compute Q, right? We don't need it afterwards. So this is sometimes called slicing, program slicing, when a program computes several things and you're only interested in one. Just remove all the parts of the program that don't contribute. And that's exactly what we have been doing here. So that's pretty neat, I think. And yeah, so this is the same in a slightly more readable syntax. However, if now we are interested in Q, in the quotient, but not in the remainder, then unfortunately there's nothing we can optimize because the remainder R is used as a stopping condition for the loop. Okay, so it must be computed and updated at every iteration. Okay? Let's see, do I have more examples? No. Okay, and now of course the question is the correctness of this transformation. So is it really the case that those two programs compute the same things? Well, obviously not. This one computes Q and this one doesn't. But at least if all we are interested in is the value of R, do they compute the same thing? And that's what we are going to prove now. And before we can prove something, we need to understand what we want to prove. And we need to think for a while about liveness. So what does it mean semantically for a variable x to be live at a program point? And there's no obvious answer because, as we saw, liveness is an approximation. Okay, it's an over-approximation. So it means that, well, x may be used in the future, but maybe not. However, if we negate the question, okay, so sorry for this is kind of classical, but never mind. If we negate the question and ask what it means for a variable to be dead at a program point, then we have a clear characterization. It means that its value, its precise value, has no impact on the rest of the program execution. So you could use a debugger, stop the program at that point, change the value of x, good debuggers let you do that, and restart the program, and nobody would notice. Okay? And really, liveness can be viewed as a so-called information flow property in the sense that, so we'll consider two executions of the same command, C, but in different initial states. Okay, so this one goes from S1 to S2, and this one goes from S1 prime to S2 prime. And what we will show is that if the two initial states agree on the variables that are live before C, basically they assign the same values to those variables, but they can assign different values to other variables, then both executions will terminate on states that agree on the live variables L after C. Okay? And again, maybe other variables will have different values. But yeah, so that is the semantic property of liveness analysis. And we are going to show it and use it to prove semantic preservation for dead code elimination. Only instead of relating two executions of C, we are going to relate an execution of C and an execution of the optimized version of C, the one that has that underwent dead code elimination. So this is agreement, as I said. So two states agree on a set of variables if for all x in that set, S1 of x equals S2 of x. And it has some cool properties. Of course, it is monotonic. So if you agree on a big set, then you agree on a smaller set. And then if you agree on the free variables of an expression, then the expression evaluates the same in both states. Likewise for Boolean valued expressions. And here are really the two key properties. If you do parallel assignment to a variable, so you assign the same value x to the same value v to the same value x in both programs, then you will agree on L, provided before you agreed on L minus x. Okay, you don't have to agree on x before, because here you're assigning the same value on both sides. However, if a variable is dead in R, then agreement is preserved by unilateral assignment. Okay, you can assign in S1 and do nothing in S2, and agreement is preserved. And that's exactly what happens when we optimize in DCE. So here we have an assignment, and there we have a skip that doesn't change the store. And just with those four silly lemmas, well, we can show forward simulation. So here the proof that uses big step semantics. So for terminating source programs, we show that if the source program goes from ST to ST prime, and ST and ST1 agree on the variables live before, then the transform program, DCECL, which is the optimized program, started in ST1, terminates in some ST1 prime that agrees with ST prime over L. So that is this commutation diagram I showed you. Again, these are our hypotheses, and these are our conclusions. And the proof is a really simple natural induction on this evaluation derivation. Well, you can look at it in the code development. But again, yeah, basically these are the essential lemmas that you need to treat assignment, and these are the essential lemmas you need to treat in particular if and while. You believe me? Okay, I'll take that for a yes. And you can even prove that for divergence as well, using, for instance, the co-inductive big step semantics. So if C started in ST diverges, and ST and ST1 agree on the variables live before C, then the optimized code DCECL started in ST1 diverges. And we don't have anything to say about the final states because they are known. Okay, the good thing about divergence, you don't care about what's going on after. Okay, we'll all be dead anyway. So, and if you're looking for exercises, it's interesting to redo that proof using other styles of semantics. So you can do it with the small step semantics. You can even do it with the denotational semantics that we saw yesterday. And those proofs work pretty well. For small step semantics, you get the lockstep simulation diagram, okay, the kind that is not too hard to prove. And you can conclude the same semantic preservation. All right, so what did I wanted to say? Yes, I wanted to come back to fixed points, but yes, the other question here.
In real life, in ComCert, when you do another optimization pass, do you have to redo all the proofs for small step and big steps?
No, in general, well, no, I do the proof for only one semantics. And ComCert nowadays using small step semantics, uses small step semantics throughout, just because, as I said yesterday, you only have one proof that applies both to the terminating and diverging cases, and that is the net gain where you have maybe 12 or 20 different constructs in your language, and when your language gets bigger. No, this is purely for pedagogical reasons. I mean, I'm willing to believe any one of those proofs. Okay, and yeah, so now I would like to come back to those fixed points, and we are going to do some a little bit of advanced Coq programming and proving to try to work with this Knaster-Tarski fixed point theorem. So I've stated it again here. So you have a functional over an ordered type. Functional is monotone, increasing, and your type has the ascending chain condition. Then you can compute effectively a smallest fixed point. Let's do that. Let's do that. Yeah, just before, a few words about the ascending chain condition in Coq. So it is an instance of so-called well-founded orderings. So I think Greg Morissette used that in one of his lectures, the one with the unification algorithm. Basically, it's a generalization of like induction over integers, right? And so well-founded ordering, R, is a relation between over type A. And you want to say that there are no infinite chains like this. So if you start from X and then have an X1 that is smaller, so let's read R as strictly smaller. Smaller, bigger. No, I talk about the ascending chain condition, so bigger. Okay, so you start with X, you have a bigger X1 and a bigger X2 and a bigger Xn, and you want to show that this cannot go on forever. So you would be tempted to write some very negative characterization, okay? It is not possible to have an infinite chain. But Koch likes you to think positively. And so actually, the way to express that in Koch is to say that from X, all chains like this are finite, eventually bottom up. And for that, there's this incredibly powerful inductive predicate that says ACK of X holds if for any y that is bigger than X, y is itself accessible. Yeah, ACK means accessible. And since this is an inductive predicate, okay, you can only apply this ACK intro rule a finite number of times to, well, you may apply it infinitely often. I mean, this is infinitely branching in general because of this for all, but still every path in this derivation must be finite. And so this means that from X, okay, basically this predicate captures all chains, all ascending chains rooted at X, and the fact that it is inductive guarantees that they are all finite. Okay. Don't worry if it is mysterious. It takes a while to understand this. I'm not sure I've completely succeeded. But anyway, and then we say that an ordering is well-founded if all elements of A are accessible. Okay. So not only you get a positive characterization of this ascending chain condition, but you even get an induction principle, which is the induction principle corresponding to this inductive type. So I'm not going to write it down, but it is exactly what is called Noetherian induction in mathematics. Basically, if you can prove something, assuming that it holds for any strictly bigger y, okay, and then you can conclude that it holds for any x. Okay, so yeah, well. And here are some examples of well-founded orderings that are often used in Koch developments. So a simple one is over natural numbers. So here we are not increasing, we are decreasing. Okay, and so of course eventually we bottom up at 0. Here is another one where we're increasing, but no more than some constant n. So again, we can't go past n. This is perhaps the most useful. So if you have a measure, a function from A from your type of interest to nat, and you order elements of A by their measure, okay, then you get a well-founded ordering. The lexicographic product of two well-founded orderings is also itself well-founded. There are some other constructions like this that let you compose well-founded orderings. Okay, so now let's switch to Koch and see what we can do with that. We can compute fixed points. And here is how. All right, so I start with some type A. It has a decidable equality. So EQ is the equality. BEQ is a Boolean valued function that decides it. Okay. LE is less than or equal, is my large order, which must be transitive. Then we define the strict order greater than, that is induced. So x is greater than y if y is less than or equal to x and y and x are not equal. And we assume that this ordering is well-founded. Okay. We have a bottom element of A. We have a monotonic function from A to A. So if x is less than y, then f of x is less than f of y. And now this is the iteration I mentioned. the Knaster-Tarski iteration. However, it's not your ordinary function because it's not. So it's going to take x, the starting point for the iteration, as argument, but also two preconditions. So two arguments of type prop. Two proofs of those propositions. One is that x is a prefix point. So x is still less than or equal to f of x. So we haven't reached a postfix point yet. And the other one says that x is smaller than any postfix point. So we will need that to prove that we are computing the smallest fixed point. So we are going to take those three arguments, two of which are proofs of logical properties. And then this is not a regular fixed point. It's not structural induction. It's well-founded induction, Noetherian induction. And it's kind of hard to use by hand. However, Coq provides a nifty system called program. I don't know if Mathieu is here today. Well, the author of program is, oh yes, so the author of program is here. So if it doesn't do what you want, ask him. No, sorry. When it doesn't do what you want, ask him. So basically, this is going to generate a lot of things under the hood that will implement Noetherian recursion, so that is very nice. And likewise, this is not an ordinary function because it's not just going to compute a result of type A, but also two proofs of properties about this A, this y of type A. One is that it is a fixed point, so y equal f of y, and that it is the smallest post-fixed point. Is that? Yes, exactly. And so this is captured with this funny curly bracket notation, which I will explain in more details later. But for now on, just think of that as a value of type A plus proof that it satisfies this property. OK, and now this is the body of the computation. So we compute f of x with x prime equals f of x. If x is equal to x prime, then we found our fixed point, so we return x. Otherwise, we iterate again, starting with x prime. And remember, this function takes three arguments, a real value and then two proofs. And I really don't want to write proof terms by hand. Okay, so program lets you just write underscores. And then it will drop into interactive proof mode to tell you, OK, now let's prove something that will fill that hole and something that will fill this hole. And there's even a third hole that you didn't see, which is that here I'm returning an x as a result, but I also have to prove that this property holds for this particular x. So normally, if everything goes well, program fixed point, yes, I retract. Program fixed point should leave me with three proof obligations. Again, we are patiently waiting for this little MacBook to work. OK. All right, so let's have a look at this. Oh, 4 obligations. Ah. OK, so much more. OK, so obligation number 1 is saying that the post condition here is true when we return x. This is obligation 1. Obligation 2, it solves by itself. Good. Obligation 3 is obligation 3 is that we are still below any fixed point. So obligation 2 was this hole, and it found it all by itself. Obligation 3, this hole. And obligation 4 is that we recurse on a strictly greater x, okay? Because, well, this is well-founded induction, so we can only recurse if we respect the ordering. All right, so, well, all those obligations can be proved, again, using interactive proof mode. That's not too hard here. And after that, finally, iterate is defined and with the proper type. And now we can define the fixed point as iterating from bottom, with bottom as a starting point. So again, there are two proof obligations here to provide, but they are so trivial that program fixed point finds them by itself. And we can show that, well, since it is a result of iterate, it satisfies its post condition. So it is a fixed point, and it is the smallest post fixed point, and in particular, the smallest fixed point. Okay, so that was cool. But still, we have some work to do before we can apply this to our static analysis. Because, as we saw earlier, we need to work over sets of variables that are ordered by inclusion. But unfortunately, there's inclusion in the wrong direction. Okay, there's inclusion where sets grow and grow and grow and grow. And so to show that we cannot have infinite ascending chains, there are two facts we need to exploit. One is that in any given program, there's only a finite number of variables that are mentioned. Okay? And second, that liveness analysis manipulates only subsets of this universe, finite universe of variables. It's never going to invent a new variable that is not in your source program. Okay? And now we have some hope to have, well, now inclusion will, I mean, if we have a strictly ascending chain like this, but all those sets are subset of this set, then it must eventually stop. And so that's what we want to capture. But it is going to take a little work. So let's say that U is this universe of variables. That's all variables appearing in the program we analyze. And so now we are going to define the set of the type, V set, of subsets of U. And one way to do it is to use these curly brackets, which is really a notation for a Coq inductive data type. And that really reads, V set is a type of S that have type Vs.T, so of finite sets that satisfies this condition, that are subsets of U. Okay, and maybe I have that on my slide. Yes, so actually this is not built into Coq, it's just defined in the Coq standard library. So it is syntactic sugar for this sig type, which takes type, the type of elements, and the predicate that must hold about them. It has exactly one constructor. It takes an x, which takes an x of type A, and dependently a proof that P of x holds, and returns a value of type sig AP, or x of type A such that P of x holds. And so it looks very much like a pair, and indeed there are two projections. The first projection is going to extract the A, the underlying value, basically that part here. And the second projection is going to extract a proof that the first projection satisfies P. Okay, so that the element you just extracted satisfies the specification. So that's a very useful type to have. And so for our set, so this is how we construct a V set. We give it a carrier, just a plain set, and then evidence that it is a subset of U, and that gives us a V set. This is the first projection, which is a carrier of our V set type, so it gives us an ordinary set. And this is the fundamental lemma that says that the carrier of X is always a subset of U, and that's just a second projection applied to this type. Okay, so far so good. But now we have to define, I mean, operations over sets, plain sets, just no longer work, okay?